Hi, in today's video, we'll be going through the principle of inclusion and exclusion. This principle is like an extension of the addition principle. Let's see why is this so before stating it fully. Well, intuitively, if you know that A and B are disjoint sets, then by the addition principle, the number of ways that A or B could occur is just adding them up. But if now, let's say the A and B, the intersection is no longer empty, then A union B must equals to A plus B minus way A intersect B, all in cardinality, of course. And let's see why is this so. Well, if you see the Venn diagram, you want to add the elements that is in A, not in B, A in N in B, and in B but not in A. And now these are just disjoint sets. And so when you add them up, you can just use directly the addition principle. And so what is in A but not in B? That will be the A minus the way the A intersect B. Then you add the A intersect B, then B minus the A intersect B. So actually you can prove this formula by the use of addition and complementation principle. And so you get the end result is A plus B minus way A intersect B. Now, let's see an example of its use. If we have a set with from 1 to 500 and we want to know which are multiples of 4 or 6, we can just form the following: set A as the multiples of 4, and so that is the floor function of 500 over 4. The multiples of 6 as B is 500 over 6 floor function. And the multiples of 4 and 6, and since the greatest common divisor between them, the lowest common multiple between them is 12, it's just forming the multiples of 12, which is 500 divided by 12, floor function. Now, A union B is just adding A plus B minus way A intersect B, which is 167. Next, we want to do for more than 2 sets, 3 sets. And so, it's basically the same idea. You add A, B, and C up, then you see that these parts overlap, and so they have been repeated. So you minus off this, this, and this. But after minusing off 3 times and adding, and at the start you add 3 times, you have minus away this 7 in total. So you need to add back the 7. And so it's the thing where you add everything, then you minus away all the intersections, then you add back all those that you minus too many, and then it reaches the end at the end. And this proves that, well, it actually counts everything without overcounting or undercounting. And so you can generalize this for Q sets. And so the union of Q sets is you add everything minus away all pairs plus together all triplets that you can form. Then you can, and then you minus, and then plus minus 1 to the power of Q plus 1 times the intersection of everything. Now, we move on to the generalized principle of inclusion and exclusion. That not deals with just a union, but it can deal with exactly Q properties that you want. And what do I mean by properties? Well, for any set that is a subset of the original set, it is basically the elements satisfying some predicate. And so this predicate, you can think of it as the property P. And so X is an element of A if and only if the predicate is true. So that means X has a property P. For example, if S is 1, 2, 3, 4, 5, let the P1 be the property of being a prime, P2 be a property of non-prime. Set A is that P1 holds, that means it is a prime, so it's 2, 3, and 5. Set B is the property P2 holds, and so that's non-primes, which is 1 and 4. So these are just some notation and definition to get us starting to understand the generalized principle of inclusion and exclusion, GPIE. And that is, we have a set with n elements, and you have Q properties over here. Then you want to know how many of these elements possess exactly M. In this case, it's like a union, so it's like you can have property 1 or 2 or 3, but you could have all 3 properties. So that's not exactly, because it's exactly 1 property. That's like you can have 3 properties or 2 or 1. But now you want to know what happens to have, you want to find the number of ways to have exactly m. And because it's exactly, if you want to know 1 or 2 or 3, you just need to add 1 plus 2 plus 3 using the addition principle without minusing f anything, because they are already going to be pairwise disjoint. It does not say which elements have what properties. That's the thing to remember. It just says this element has 2 of these properties, and so it's inside this set. For example, let's say property X has P1 and P2, and property Y has Q minus 1 and Q. Then both have exactly 2. So it's inside this EM set. We let W, P1 to Pm be the elements that possesses the properties P1 to Pm. Then Wm is just the summation of all these combinations of m that you can form. For example, if you have n elements, then the number of combinations of m properties is n choose m. And so you need to take all these combinations of this different n choose m number and add them all up to see what is this Wm. So the WMP, W bracket P's inside is the number of elements that have these P properties. And then Wm is just adding all these m combinations up. Then Em, which is the number of exactly m, is just given by this formula. And let me explain to you why intuitively this is so. Well, you take, for example, you want to know the elements with exactly m. That's obviously going to be all those elements with m properties first. So that's Wm. But then from these m elements, you need to minus off m plus 1 choose m of Wm plus 1. Because what does Wm plus 1 state? Wm plus 1 state is the number of elements that possesses m plus 1 properties. Okay? So this is going to be a little tricky, so you got to listen carefully. Wm is the number of elements that possess m properties. But these elements, it possesses, like, let's say, okay, let's say you have P1 and P2. You have P1 and P2. So P1 states that you have property either P1 or you have property P2. And P2 is you have property P1 and P2 at the same time. But this element has P1 and P2 will of course have the element that is in P1. So and it will have it will also be counted in the element that has P2. Can you see? So Wm is not the number of elements that have exactly one property. It is the number of elements you add them up. If it has P1, then it's added. It has P2 is added. But you can see that if it has the properties of Pm plus 1, it is added m plus 1 choose m times. Okay. So like 2. So in this case, if you have 2 properties, then you're added twice when you are counting the one property case. And so you need to minus off m plus 1 choose m of Wm plus 1. But then of course you overshot, and then you need to add back the m plus 2 choose m of Wm plus 2, because with m plus 2 properties that appeared, obviously it appears also in the m times. But since you minus, but then it also obviously happens in the m plus 1 times that you minused off, so you need to add them back, and then you repeat this property until the nq. And so you get this nice formula from the summation of m to q of minus 1 to power k minus m. K choose m, wk, or you can think of it as from 0 to q minus m, minus 1 to power I, m plus I choose m, wm plus I. And so we'll use an example to further illustrate this. For example, you have 14 elements with 4 properties. Then those with just property 1 are 1, 4, 8, 9, and 12. Those with P2 is 1, 2, 3, 4, 6, 8, 10, 11, 13. Can you already see that if you are in P1 and P2, which is having these two properties, meaning you want to see this, they are counted twice in P1 and P2, like I said earlier. And so that's why you're going to need to minus P1, choose P1, P2, you got two options, you choose one because it will appear here and here 2 times. So you use the formula and you can see E1 is 4, E2 is going to be 4 also, E3 is 2, E4 is 2, and then E0 is just the total set minus all this, which is just going to be 2. It's worthwhile to note that actually W0 is defined to be then the total set, because you can see that E0 will be in the end taking the total set minus of all the previous sets. And so W0 in this case has to be defined to be n for it to make sense. And so you can see how the general principle of inclusion and exclusion works, and I hope you have understand what I was trying to say. If you can't, you can read more online or you can replay the videos and I'll share these notes with you. But let's continue. So now let's find the number of integer solutions to this equation. But now these properties are less than n. So it's n here. But it's hard to count if it's less than. So let's make it let's create a property to be greater than, so that you can just fill in 6 here first, then you choose again. P2 is 7 and P2 is 8. So if you want to have a property that does not have all these properties, so that's E0, and that's W0 minus 1, 2 plus 2 minus 3. What's W0? It's the total set, which you know it's 15 plus 2, choose 15, minus away. Now you give 6 to E1 already. You left with 9, so you plus 2, since this is the 2 pluses, which you can think of them as the lines, which is the stars and bars technique taught in previous videos. Plus 10 choose 8 plus 9 choose 7, then you add back 4 choose 2 plus 3 choose 1 plus 2 choose 0. But W3 is when you have P1, P2 and P3. But that's not possible because when you add them up, it's greater than 15. So that's 0 ways. And this is the number of ways to get E0, which is what you want. Now, let's move on to a more interesting example used in number theory for, I guess, combinatorics number theory, which is the Euler to Theorem function, Euler phi function also known as. So this Euler to Theorem function, or Euler phi functions as I like to call it, counts the number of co-prime integers that is less than you. Obviously, you can't be co-prime to yourself, because we say that you are co-prime to two numbers are co-prime if the GCD is 1. That means the greatest common divisor is 1. That means there's no common divisors between the two numbers. So you can see this is a list of it, and you can check. 1, 3, and 7, and 9 do not divide 10, because 2 don't have any divisors with 10. Because 2, 4, 6, and 8, they all are divisible by 2, and 10 is divisible by 2. And so you want to calculate the number of co-prime elements that is less than you, or between the elements between 1 to n. Now, we want to prove that this is the formula, and which is just n times the product of 1 to k, k being the greatest, the number of primes that divides n, then 1 minus 1 over pi. Well, why is this formula so? Let's prove it using the help of the generalized inclusion and exclusion principle. Let's take the elements from 1 to n now. At n having a prime factorization, which is unique, of p1 to the power m1 times all the way pk to the power mk. You let capital Pi be the property that this little pi, which represents the prime, divides an element x, and x is one of the elements from 1 to n. Then, because if you are co-prime to n, and because you are less than, you can't be divisible by any of these primes as well. Because if you're divisible by one of these primes, then your greatest common divisor will be one of these primes already. And so you want to have E0. So it's none of this property, not being able to divide by any of the primes of n. And so what is W0? W0. So E0 is just W0 minus W1 all the way to plus minus 1 to the power k, Wk. And W0, like I said, is the total set, which is just n elements. W1 is the number of primes that divide, number of elements with only one prime divisor. And so that's just n divided by pi, and then you sum from 1 to k. Then you add all those n divided by 2 of the prime divisors, and then the triplets, and all the way to k. Then you pull out the n, and this is the formula left. And then this is just the multinomial expansion of 1 minus 1 over p1, 1 minus 1 over p2, and all the way 1 minus 1 over pk. And you can check that algebraically. And so this proves the Euler phi function. And you can see it's not that hard to prove once you use the generalized inclusion and exclusion principle to add, subtract, all the way in. And then you factorize them out. So this is one interesting fact about the number of coprimes between 1 to n. And I hope you have enjoyed this video. Please feel free to like, share, and subscribe, and comment on any other videos on counting that you wish for me to do, and I'll do it. Thank you.